Hi, my name is Banghua, and today I'm honored to share our recent submission on EC on the sample complexity of online contract design. This is joint work with my co-authors Stephen Bates, Zhuoran Yang, Yixin Wang, Jiantao Jiao, and Mike Jordan. So in traditional contract theory, a principal will hire some self-interested agent to work for her based on some pre-specified contract. In an online crowdsourcing platform like Amazon Mechanical Turk, the principal will interact with agents in multiple rounds. So in this case, we ask the following question. How many samples do we need to learn a near optimal contract? So the formulation starts with a static model where the principal comes with a different value, that is m-dimensional vector V for m different outcomes, which is O1 to OM. Based on the different values, the principal will propose a contract that specifies a payment for each of the outcomes. So the contract will also be an m-dimensional vector. The agent will then choose from n actions, each associated with a probability distribution supported on the simplex of m dimension, which is the probability of outcome for each of the actions. And the cost function will be associated with each action, which is a scalar. The agent will choose actions to maximize her own utility, where the utility is defined as the expected payment from the contract, which is the inner product between the probability of actions and this the probability of outcomes based on the actions and the contract itself, F. And the whole utility will also subtract the cost for each different actions. And finally, the agent will make decision on the choice of actions based on the action that is maximizing the so-called this defined utility. After the agent takes actions, the principal will receive some outcome that is sampled from the probability distribution of this optimal action. And eventually, the principal will receive her utility function, which is the value of this outcome, subtract the payment for this outcome, which is basically VO minus FO. So we can extend the static model to dynamic model by considering a multi-round interaction case. So at the beginning of each round, the principal will offer the agent a contract. And in this case, the party will have symmetric information. And this contract can be based on all the past observations in the previous round. And this is also inside a set capital F that is a subset of this m-dimensional vector in 0 and 1. And after the principal offers the contract, the agent will take actions according to this contract by either accept or refuse. And in the case of accepting, the agent will also take some actions based on the provided contract. So in this case, again, we have this probability distribution of actions, that is the probability on the outcomes. So it's m-dimensional. We also have a cost function that maps each action to a scalar. And the agent will try to takes action that maximizes her own utility function, which is the expected payment subtract the cost. And the agent action's outcome will reward the principal back by first sampling an outcome from this probability distribution, and the principal will receive or get payment from the or pays agent and receive some utility function, which is the value of that outcome, subtract the payment of that outcome. So in this case, our target is to design an algorithm based on historical observations of past contracts and outcomes, such that the stackable regret can be minimized. So the stackable regret is defined as a case where I compare my utility function introduced by my algorithm pi with the optimal utility function that is induced by the optimal potential contract F, where this utility function is the utility for the principal. But we also notice that in this case, the action is always an optimal action that maximizes the agent's utility. So that's why we call it a stackable regret. So our main result is following. So we provide a bound for the stackable regret when the contract family F is either the general contract family, which is the m-dimensional vector where each of the coordinate is supported in between 0 and 1, or a linear contract where your contract is restricted to be just a scalar times your value function, and you can only change your scalar alpha here. So we show that in the case of general contract, with the m-dimensional general contract, the stackable regret can be upper bounded by t to the 1 minus 1 over 2m plus 1, and lower bounded by t to the 1 minus 1 over m plus 2. And in the linear case, we can show that the stackable regret is exactly theta t to the 2 to the 3. Sorry, 2 over 3. And we show that it requires exponential samples to learn a near optimal contract when we have a general contract space. However, when we restrict ourselves to the family of linear contracts, we only need a polynomial number of samples to learn a near optimal contract. So when compared with the previous bound, our upper bound for the general contract actually removes all the assumptions in the prior work, including a discretized contract space and also a monotone contract assumption. In terms of the lower bound, our lower bound actually settles down the sample complexity and the difficulty of learning this optimal contract, which resolves an open problem proposed in the same paper. So below is a very straightforward sketch of our analysis. So our key observation is the continuity of the utility function in the stackable game. So due to this max operation, where the agent will always maximize her own utility, the principal's utility function is usually not a continuous function of the action of the principal, which is in this case our contract choice. However, we identify a specific direction gamma such that under this direction of gamma, your utility function is indeed continuous. And it's continuous in a non-straightforward fashion in that our gamma need to be decomposed into two directions. One is a direction of v minus f that depends on both v and f. And the other direction is anything that is beyond this v minus f direction. And eventually our continuity bound actually depends on both the infinite norm of R and also this fraction of R. So from image, we can actually show a more straightforward interpretation of this lemma. So we show that this utility function is only continuous along specific directions, which is a cone that has a center in this V and F connection. And then we show that if we want to discretize the whole cube space, and for each of the points that we choose in the discretized space, it will cover a cone that like this. And then we can cover the whole cylinder with several cones. And then we can use this several cylinders to cover the whole cube. So the whole procedure is achieved by the spherical code, especially like introduced in the third step. And eventually we introduce a new way of covering the whole cube, just starting from this cone. So we show that for any contract space F, so as long as it can be epsilon covered using the previous method with this n cones, and we also assume that this number of cones actually grows exponentially with some hidden dimension d. And then the sample complexity we show will be t to the 1 minus 1 over 2d plus 1. For the general contract, we can show that this d is upper bounded by n, which leads to a sample complexity upper bound, which is t to the 1 minus 1 over 2m plus 1. And for the linear contract case, the dimensionality d is 1, which will give us the tight upper bound t to the 2 over 3. So for the lower bound, we basically split the whole space, this m-dimensional cube, to 1 over epsilon to the n disjoint cubes. And you select one cube to have slightly higher utility, while the other stay the same. And eventually, we apply Lecomte's two-point method to get our lower bound. In terms of future work, the first open question we would like to point out here is that during our construction of the lower bound, we always construct a special case where the action set n is actually exponential. But this lower bound will not hold when the action set n is small, which meaning that the sample complexity when the action set n is small is still largely open at this point. We're also interested to see whether it can be extended to other contract design formulations. And we're also eager to see the connections between this work and more continual unbounded problems, along with general stack overgain. Thank you for your listening.